Hi, questions in analysis. Let C denote the cardinality of the continuum. Question 1. Let A be the set given by this one, where I is an index set. Prove that if the cardinal number of I is equal to C, then the cardinal number of A is equal to C. Solution. Suppose that the cardinality of I is equal to C. Define a member phi by this one. Then phi from A to phi A is a bijection. We knew that this cardinality is equal to C. So we have this inequality. Since the cardinality of I is equal to C, the cardinality of phi A is equal to C. Consequently, the cardinality of A is equal to C. Question 2. Let xn be a sequence of real numbers. Let C be the collection of all subsequences of the sequence xn. If all the elements xi of xn are distinct, prove that the cardinality of the collection C is equal to C. If only a finite number of elements xi of the sequence xn are distinct, what is the cardinality of the collection C? Solution. Case 1. Suppose that all the elements xi of the sequence xn are distinct. Write a subsequence given by this one. Define a mapping phi given by this one. Then the map phi from C to phi C is a bijection. We know that the cardinality of the open interval 0, 1 is equal to C. So we have this inequality. Consequently, we have this inequality. Recall a previous video. There does not exist a function from the sequence xn onto C. This implies the cardinality of C is greater than of nu. We conclude we have these inequalities. This implies this result. Case 2. Suppose that only a finite number of elements xi of the sequence xn are distinct. Note that any finite decimal r is a rational number in the interval 0, 1, and q is countable. So phi c is countable. Consequently, the collection C is countable. This implies the cardinality of C is equal to or less than of nu. Question 3. Let C be the collection of all monotone and continuous from the right real functions defined on the closed interval AB. Prove that the cardinality of the collection C is equal to C. Solution. Note that a constant function is in the collection C, and the cardinality of all constant functions defined on the closed interval AB is equal to C. This implies we have this inequality. Write the intersection of Q and the closed interval AB by this one. For any x in the closed interval AB, there is a sequence given by this one, such that we have this limit. For a function f in the correction C, we have this limit. This is f is completely determined by this set. So we can define a member phi by this one. We see that the member phi from C to phi C is a bijection. This implies we have this inequality. Consequently, we have this inequality. We thus conclude the cardinality of the character C is equal to C. Let M be the collection of monotone functions defined on the closed interval AB. We have this inequality. Here is the remark. Question 4. Let AN be the subsets of the real field R. Prove that if the cardinality of this union is equal to C, then there is a 1 of AK. Its cardinality is equal to C. Solution 1. Suppose that the cardinality of this union is equal to C. By the continuum hypothesis, the cardinality of A1 is equal to C, or the cardinality of A2 is equal to C. Case 2. Suppose that is equal to C. By the continuum hypothesis, the cardinality of AK is equal to C for some positive integer k. Thanks for watching. Bye.